I was just going to go through literally on the last slide things. I don't remember this from class, but I guess it was there. There's like a list of 5 things from this section.
Over a week ago.
Okay. There was a list of 5 things from after the quiz that he said no for the final.
Oh.
And there was literally 5 bullet points.
All right.
I don't know. I don't remember. It was just, it's on the most recent PowerPoint
Is
on
this
Blackboard.
ringing a bell for you?
No.
Me neither. Okay.
Yeah, that's what I was going to say. I literally have no memory. If you just go on Blackboard on the last slideshow that's on there, it's on there at the beginning.
Okay,
And I'll just go through all of those things. They're just the things that are on the homework.
Yeah, that's fine.
But I'll just go over it because
That's awesome.
this equation will solve like 90% of the homework probably.
My
Right.
entire life.
Equals
minus 5.
HC over lambda. Hopefully this marker is, yeah, that's fine.
Is your V an F technically?
V,
Sorry.
no, it's,
I'm not
no, these, you just really shouldn't, okay. This is a new,
Oh,
new
it's
is
new.
frequency.
Oh, okay.
You really
Oh.
shouldn't use F.
Okay.
Do they use F in the book?
Yes.
Really? That's really annoying.
I betcha.
Okay, well I guess it's F. So F is the frequency, I guess it's F, which is also, so remember V, velocity? So, sorry, don't write this down because I'm going to erase it because it's also confusing because it looks like a new.
It does.
So V is the velocity of a wave, remember we talked about this, is F lambda, right? It's the frequency times the wavelength. That's just true for any wave. But all, these are always, they're for photons, so they're always traveling at the speed of light, which we call c.
Mm-hmm.
And therefore, c over f is lambda.
Okay.
So we can always just use this relation. Now, in everywhere in the entire world, they use nu, which is a Greek letter, right? It comes after mu, for frequency. Except for here, where they use f for some reason. Now, I don't like that, because I don't think it's, I don't like it. But anyway, I guess it's the same thing. But the point is that you can use this relation for photons always, because it's, all right, I know the people on the video don't like the other colors. Oh, okay, I guess I see why. All right, never mind. Oh, so they told me where to find, whatever. Oh, they told me there was somewhere in the front that had markers.
Probably
There's
the
a
fishbowl drawer. Oh, the drawer.
It might have been locked.
Do you
What
want
about the ones over there?
That's all right. I checked some of those. I mean,
The ones over there?
Do you want more black?
yeah. All right,
Always.
I'll go check it in the front. I don't really actually remember where it is.
How long were you in Connecticut?
I didn't go to Connecticut. We just moved to Plymouth, so I was there.
Oh, they bought a new house.
Yeah, so we spent Thanksgiving surrounded by boxes, but it was really nice.
Here we go. Okay. This is like not good either. But
It's the same.
all right, that's fine. I should just buy a nice one and keep it.
You know what? If they want to see it, they can make it. Don't put that in the
Wow.
video. That's a joke.
It's been
I-
recording.
It's
so-
already recording.
Oh well.
Yeah, but I'm assuming you're gonna edit most of this
I-
out.
I'm
Okay, so no, I don't do
Not
anything.
everybody can make an effort. I only came because I took off work. So
We understand. Life is challenging.
All right.
they can't.
So E equals
Hopefully
H.
that's,
Sorry, yeah.
Anyway, so H is a constant, C is a constant, HC therefore is also a constant,
Mhm.
and therefore there's only literally one variable in each of these. If you have the wavelength or you have the frequency. So I guess I'll write F here.
Yep. Sorry, Keegan. I
To
know that
Fix
pains you.
it. It's just not really, okay. Anyway, and then they have the same relation. And of course, because photons have to travel, they can't be at a different speed. There's sort of all these reasons, but I wish we could go into, but I can't really, about why they have to travel at the same speed, speed of light. So they're related just by a constant. Then, so this is like kinetic energy, right? Because these are, well, okay. So if you shine photons at a piece of metal, this is one of the things that they do in the book and in real life. If you shine photons at metal, you will get that electrons radiate off of it, right? And the electrons get radiated off with some kinetic energy. Of course, electrons can have kinetic energy separate from their mass and all that stuff, right? So they have kinetic energy, which is equal to the photon energy that they sort of, absorbed, minus the energy it took to liberate them from the bonds or whatever they're called. So that's called the work function, phi, capital phi, I think they use.
Yes.
So, yeah. So E photon is just the energies of the photons you, and of course, if you shine photons at something, the energy you shine it on is, now this is for one electron, obviously. This is all for a single electron with a single photon. And this is just H, I guess, F, right? Or you could, of course, say HC over lambda. And this is the kinetic energy of the electron. So this process specifically is called the photoelectric effect, but this is specifically in a metal, or really it doesn't matter. It's just any time an electron is bound by some thing that costs some energy, phi, to free it from, like it's like on an atom, right? Costs some energy to ionize an atom, to take an electron off, and that's just this energy here. So if you shine if you have a photon with energy that's not as much as the work function, you don't even have enough energy to get it free of the atom. So that's the whole point of the photoelectric effect, is that if you shine it with frequency low enough, none of the photons will be able to overcome any of the electrons. So depending on, you could look up the work function for different metals, I guess it's different amounts or whatever. And if you have a frequency less than that, you will get 0 electrons flying off it. But once you cross that, you will get some, and they will have some kinetic energy, which is just the leftover energy. So this is very sort of intuitive. It's it's not anything like it seems. It's in the quantum chapter, so I think they want you to be like, oh, it's crazy. This is pretty intuitive. It's just the weird part is that you get literally 0. It's not like when you turn the intensity down, you get less and less and less. It doesn't go to 0. It stops immediately as you get frequencies lower than the threshold frequency or whatever. So you could solve the threshold frequency just with this equation. And what's actually happening is described by the Compton scattering or something. The Compton effect, maybe. Actually, that might be something else. But anyway, so this is what happens, right? You get an electron that was stationary, and this is a photon with a lambda, and this is a photon with a lambda prime, and they interact at this point. Now this is a section, this picture here is really interesting, but not the way they talk about it, but not that it's boring. It's just that this is much more interesting than they say, which is they call it Compton scattering, and that was described, and that has a bunch of angles and stuff in it. This is actually an interaction from something called quantum electrodynamics, which is the theory that governs how photons and electrons interact. And you get this is much more interesting to talk about. But anyway, what happens is that because of the momentum, so this is kind of it's like a proof that that photons have momentum, because the electron was at rest at the beginning of this, and then this is a collision, right? The electron was at rest, and the photon came in, and you might think, what if the electron wasn't at rest? Well, you can always just go to a reference frame where it's at rest, so don't worry about that. So the electron was at rest, and then a photon hit it, and then the electron flies off, and the photon flies off at some angle. So this is sort of proof that there was some momentum transfer. In the original case, the electron was stationary, it had no momentum, and so the only momentum in the system was the photon. And of course, because of this, you can tell that it does have momentum, and the lambda prime, so it also has a new wavelength here. So that also tells us that the momentum is related to the wavelength, right? And so, and it's related by minus, is it minus? Yeah. Wait. Oh, it's plus. H, they might write it slightly differently. MEC. Me is the mass of the electron. Times 1 minus cosine theta. Okay, they probably read it like this. This is the equivalent way to write it. It's just the difference in the wavelength. So the change in the wavelength is related to some constants divided by the mass of the electron, which is a constant too, I guess. So this is all a constant, and then it's related to the angle. So this also tells you, this kind of looks like a momentum type problem where you have some kind of scattering at an angle or whatever. Anyway, so this is called scattering, specifically Compton scattering. It doesn't really apply to anything else other than photons and electrons. But yeah, and now because we have lambda, so this is given to you because it's just a function that's been tested, a formula that's been tested. Because we have the lambda before and lambda after, right? The lambda before is just some constant. Lambda after is related to it by this plus that. We could find, and we know that the energy of a photon is related to the wavelength. And we have this wavelength here. We could solve for the energy before and the energy after, so we could find the energy change. And that is, I'm not going to write it. It's just some formula. I mean, it's on Wikipedia if you want to look up Compton scatter on Wikipedia. It's actually relatively simple. I just don't want to write it, and I actually think it's one of the homework problems anyway. So if you want to know if you did it right, you can just look on Wikipedia for the energy. And then if you want to find, of course, this is one of those things where there's only one parameter in it. There's constants, and there's a single parameter, which is theta. And so if you want to find like when something's maximized, like for example, so this might be one of the questions. If you want to find when something's maximized, when is this change maximized? Well, it's when this side is maximized. That can only happen when theta is what? Well, cosine is -1. Well, we can make it 0, I guess, if we set theta to be 90. Yeah. Sorry. No, I'm sorry. I want this whole thing to be 0. So if this whole thing is 0, that means we want theta to be, we want cosine to be 1, which is 0. So if the angle is 0, we get the change in the wavelength is 0. So if the angle is 0, just means that the photon continues. That makes sense. So if the photon just continues and hits an electron but doesn't do anything, it doesn't scatter at any angle, well, it couldn't have really hit anything, and, well, whatever. And therefore the wavelength would not be changed.
So it would be 180 degrees then. So basically, if there's no interference, if it doesn't move, if it doesn't go off course at all, then there's no interference.
Yes. Yeah.
Okay.
Yeah, it wouldn't be 180 degrees though. It would be 0 degrees. The angle is this.
Oh,
So if it traveled in a straight line, it would be 0. Yeah.
degrees, yeah.
Yeah, if it was 180, that would be so if it was 180, this would be -1, and therefore 1 minus 1 is 2. So it'd be like a
1
significant
minus,
amount.
yeah, 1 minus -1.
Sorry, 1 minus -1, yeah, is 2. And so therefore that would be the maximum amount. And that would mean that, your change of wavelength was actually double what your original wavelength was. And that just means that, sorry, that's not what it means. It means it's double this constant. But anyway, that would mean that that 180 degrees is this way. So it means it scattered and sort of went backwards. So you'd expect it to be sort of the maximum, negative amount. Anyway, and so that's just some formula. There might be, it's not a sort of really interesting formula, I don't think. But
So I have a question.
Yeah.
In assignment 5, it has you plug in for theta equals 90.
okay.
So then you get that your change in wavelength is a negative value,
Yes.
and you can't have a negative wavelength. So does that mean that it
You
won't?
can't have a negative one, but you can have a negative change.
I
in
can have a
wavelength.
negative change.
Yeah, because that would just mean that your new one is less than your original.
Uh,
Because this quantity is just lambda prime minus lambda, where lambda was your original wavelength. So just add whatever negative number to lambda, and you get a smaller lambda, and then that's what lambda prime is. Yeah, if you do that and you get a negative lambda prime, then you've done something wrong, because you can't have a negative wavelength.
mhm.
But you can definitely have a negative change. Yeah, right, because there's a cosine here. It would make sense that sometimes. Well, actually, hold on. Wait, you shouldn't. No, you shouldn't get a negative number.
I might have messed up.
Yeah, just because I'm thinking, because cosine is between 1 and -1, right? And so if the highest it can get is 1, 1 minus 1 is 0. Anything else is going to give you more than that, right? Like it's like 1 minus, like if you do 1 minus cosine, it looks like this, right? This is like 1 minus cosine, and it never gets below 0. So it shouldn't be a negative
I
number.
might have, yeah, that might
Yeah, I would just check your.
yeah.
It's very easy to forget, like, If it's a -1, then it's like a plus, like, so that's, yeah. So I guess you never do that. I turns out, this is Compton scattering. And then de Broglie, I'm going to say de Broglie. It's not how you're supposed to say it, but I don't want to say it any other way. So, looks like this. Well, that's how it looks. It's a wavelength that's basically when you have some particle of any type moving with some momentum p, so p is momentum, then you can define a de Broglie wave corresponding to it by just the inverse of it with h bar. This isn't a very interesting thing by itself, and to be honest, the equation is not very interesting either. But when you know, the things they talk about in the book, it's like an interesting phenomenon that you can really describe things as waves. But it's not, there's not much complication you can do to this. I mean, they write h over mv, which is like, okay, well, great, that's what p is for macroscopic things. It's not what it is for photons. For photons, it is, where can I write it? For photons, it's h bar k. These are all vectors. What else is a vector? Well, those aren't vectors. I guess that's it. So for photons, the momentum of a photon, you might think, well, momentums have no mass. But first of all, they don't have a rest mass, it's called. This ME here is the rest mass of the electron, by the way. And the whole reason that you have to say rest mass is because now we're talking about things that have different amounts of, it's basically the lowest, MEC, is the lowest amount of energy an electron can ever have. If you're in the same frame as so this is we're kind of dealing with relativity a little bit. So that means that if we're in a different reference frame, things might be a little different, like masses and energies. But if we go to the rest frame of the electron, which just means that it's stopped relative to us, we could both be moving, that doesn't matter. Then this is the lowest amount of energy that an electron can possibly have. If we move at some higher energy, we'll just get MC, but now M could be a different number and it could be a different. So anyway, it's called a rest mass. ME is called a rest mass. Oh, sorry. Well, this is really that, but anyway. I guess MC would be the rest momentum. Okay. Anyway, and then is that right? Is it H bar? Let me just check his slides. H bar K, yeah. So that was H bar. H bar is because there's a 2 pi now. H bar is H over 2 pi or something, I think. I think it's over 2 pi.
Yes, that's correct.
So the thing is, well, we'll see. At some point, you're going to start using H bar and never use H again. So just so you know. But anyway, this is H bar. The reason that there's a 2 pi involved now is because K is a wave vector. Remember, it's the same K as from waves like Kx minus omega t. It's the same K. So because that goes in an exponential for a wave or whatever, it has some angular 2 pi type stuff in it. So just if you divide it out and then you multiply by h, you get this photon momentum. That's pretty much it. You can kind of see that what's happening from here. If you see that this is the momentum of, well, okay, well, it's a little bit hard to see. All right, never mind. I was trying to say that there's a way that you can relate the collisions, the conservation of momentum in a collision, to this equation using the momentum of a photon and momentum of an electron, but it's a little bit hard to see because of this C. Well, anyway, I don't want to go into it. Anyway, so there would be some subtleties here, I'm sure. Okay. Is that it? Let me just make sure. Yeah, that's that's basically it that he said to understand on the slide things. And the rest of the PowerPoint from last class is about the Schrödinger equation, which I would love to talk about, but we don't have to. Don't.
Maybe later.
Thank you for humoring me.
Suffice to say, there's a little bit of uncertainty in discussing.
There
the
is,
Schrödinger
indeed
equation.
there is. I don't think you need the uncertainty principle for the test, by the way. I don't know if he's said anything about it. He mentioned it, I think, but I don't think he...
There's uncertainty over whether or not he discussed it.
There
Been
is.
a long time.
I guess... Well, anyway, you're going to watch like a video next class, I think. So.
We already
Is
saw
it
a
that
video.
same one of the
I don't
cartoon
think it's the same
scientist
one.
that
No,
you
I don't
Yeah, you really
like
debunked
that one.
the second after he played it?
I don't like it.
That was
Because
funny.
I don't mind that video.
That was really good. I can't lie.
It's just... It's from a... I know what it's from,
Mhm.
and what it's from is not good. And no one should watch it.
You should consider doing a video series on YouTube. Just
I am right
no,
now.
no, I mean
That's
like
You are,
just
too.
debunking like movies, scientific
Yes.
documentaries.
No, I mean, people do that, and they're kind of not a lot of fun, I think.
Well, you could make it fun.
But this, on the other hand, is not a fun movie, so I don't mind. It's... Anyway. I'm not
Okay.
going to go into it, but...
Questions.
Yes.
Is that everything that like you went?
Yeah, that was everything that was on the PowerPoint, so yeah.
So this is going into 11,
Uh-huh.
number 4, in the back of the book. So
Yeah.
it says an X-ray of wavelength, blah blah blah, is scattered by a free electron.
Yep.
So electrons can scatter wavelengths.
Yeah, that's the same thing as this. That's just this.
You talking about 8.4?
Yes.
So so this is the wavelength input or whatever, incoming, and then it scatters off of an electron. That's the same. It's all the same
okay,
thing, yeah.
Okay. Okay.
So in that case, the largest shift that could be observed with an X-ray. Oh, I see. So in that case, we just use that formula. The French name, D something.
Broglie?
Yeah, I don't
Yes.
want to butcher my French any more than I have to.
I don't even try.
So in that case,
Yeah.
We just use that formula. We just experiment with cosine of theta. And
That one is the Compton
Compton scattering.
formula, whatever. Yeah.
So yeah, the question is,
Every time they say scattering of an electron and a photon,
Mhm.
it's Compton.
Okay.
It's basically you're somehow going to use that formula, because that formula is not obvious. There's almost no way to like derive it. Well, there is, but it's not easy.
so that's the one that
It was like a Nobel Prize winning problem, so
Okay.
you're not going to be asked to derive it. But you basically need, and essentially every question will be that formula.
every
Okay.
question is going to be this formula.
No, every question about that they mentioned scattering of a photon and electron.
Okay.
So 4 and 8.
Yeah, probably. They might be like you have to do different things, like find what angle is maximizes whatever, and s minus I delta lambda. Okay.
So in that case, the answer would just be
A very small number.
something to the negative 12.
Yeah, it would be this plus.
0.7.
It'd be according to the solutions, which now that I'm thinking about it, I probably shouldn't just be saying, but whatever. This is 2.4, as you said. This is a constant, so you should keep it 2.4. The incoming is 2.4 approximately as well, or like anyway, they're very similar.
Mm-hmm.
And so one of them you get like 4.8 or so when it's 90, and when it's 45 you get like 3.1 picometers for both. So you add them in both cases. Obviously when it's 45 it's going to be like radical 2 less or whatever it is.
So this earlier you said your scattered wave is always going to be smaller than that.
Yeah. So okay. All right, we'll have to edit this one.
So,
Your scattered wave will always be have a. Oh, okay. See, I made the same confusion. Your scattered wave will always have a higher wavelength, which means it has lower energy. That's what I was confusing. So obviously, when it scatters, if it scatters at some angle, especially at a high angle, it will decrease in energy a lot.
So it generally has a higher wavelength.
So it generally has a longer wavelength. Exactly.
Is that like one of the
So that's
reasons
this.
why when you speak,
Makes
you
loads of
create a number of
sense.
vibrations, those bounce off the walls? Like when you have an echo, the voice that comes back isn't as powerful as when you're speaking.
glad I
Because it's
yeah,
been reflected
yeah,
off
it's
by
just
the-
reflections.
Okay. Okay, that's new.
And if you, at a very high angle, like 90 degrees, for example,
Yeah.
it would have it would lose a lot of energy, a lot of momentum, really, I should say, and energy too.
Okay.
But we shouldn't say it doesn't lose. Well, yeah, it's fine.
So in this case,
Just like a particle. I mean, this is how a particle would do this as well. This is a photon. This isn't like a they draw with a line, curvy line, but it's a photon, which is a particle. It's complicated.
It's not part of the textbook errata.
Oh boy.
Really? What page is it on in the book?
I feel really good.
If I'm right, 136.
You are
It
right.
says not this equation.
Correct.
Wow,
Oh,
that is
No,
weird.
it's
That is a
137.
kind of
Sorry.
annoying error.
137.
137. All right. Well,
And you've confirmed that that's what it says in the PowerPoint.
this is what it says in the PowerPoint and on Wikipedia, and therefore I trust it with my life.
Okay.
so in this case, the largest shift in wavelength would probably just be doubling it.
Say it again.
So for question 8.4,
Yeah.
it says what angle of scattering. All right. So in that case,
To do what? To double the wavelength?
yeah, it's double the wavelength. The largest
Oh.
shift in wavelength.
Oh, right. Okay, so the larger shift of wavelength would be when this side is highest,
Okay.
right? Because that's what this is delta. So when this side is the biggest number, well, these are all constants. So it's when this quantity is maximized. The most this can be is 1 minus. If this was a -1,
Yeah.
it would be 2. That's the highest it could be. So when cosine is -1, that happens when it's 90,
Okay. So 90
right?
degrees.
Oh no, sorry. Well, it's when it's 180.
180.
Yeah.
Cosine of 180 is -1, right?
Cosine of 180 wouldn't cause any shift. The 180. Oh, I see.
It would
It's
go
reflecting
backwards.
back
Yeah,
on
yeah.
itself.
Yeah, that's important to remember. The angle is here. Not if you did it the other way,
Yeah.
you
then
could. You
that's-
would just have to have it.
Okay,
right?
okay.
Yeah. So 180 is when, exactly when it's the most shifted. It literally goes backwards.
Okay. The largest shift that will be observed next with etc. Mass. All right. So the largest shift observed in that particular case for the problem is just 10 to the -12.
The amount of the largest. Oh, it would be.
What is the largest shift of wavelength if the wavelength is 1 nanometer and the electron has a mass of 9.11 times 10 to the -31st kilograms?
Then you would just. Well, the largest shift would happen when this is
Girl.
180,
Okay.
right? So just plug in 180 and plug in that mass, and those are constants, and you would get a new.
Okay. So
And plug in the original wavelength.
okay.
Yes, you just have to basically use the fact that you know what it is now to plug it in and get a value.
Perfect. All right. And for question 8.3, so it discusses what is the energy in electron volts of a photon of radiation wavelength. Lambda is equal to 500 nanometers. That's easy enough because, like we were talking about earlier, the formula for that is kinetic energy is equal to HF. So we have wavelength. We plug that into to get frequency. We multiply that by h, Planck's constant, and then we have the energy. Right?
Sorry. Can I actually see the equation? The question?
So
They did.
we're given lambda, and it
Yeah.
wants the energy in electron volts. So
Oh, I see. Yeah.
So
Okay.
we take lambda, we plug that into lambda is equal to c over f. F is
Yes,
equal to
exactly.
C.
Yeah. Or you could just use the h c over lambda, right? I
Yeah.
mean, this is just it's the same.
Yeah,
as we
same,
said,
same thing. So we do that, we get the energy for the system. All right. Once we have that,
Exactly. For the photon. For
Okay.
one photon.
so once we have the energy, it says calculate the time required for an optical field of energy density
Oh, yeah.
1 microwatts per meter squared.
Right.
Right.
1 microwatt per
Yeah.
meter squared. Okay. Well, yes. So
So find the time for that energy density to accumulate 2.4 electron volts of energy in an area of an atomic site 0.1 nanometers squared.
boy. All right. So 0.1 nanometers squared.
Yep, converting that to meters, we get
So converting to meters squared is 10 to the
-19th.
yes. So 10 to the -19.
Is this 8.3 in the text?
Yeah.
Okay.
Is it right if we just go over this
No,
quickly?
yeah. That was actually another question I had.
This is the
Yeah.
area.
Yeah, so that's the area.
Yeah.
Now, if we go ahead and we convert, I'm sorry.
So we're given lambda,
Yes.
of one photon. And
Yes.
from that, we can
500
get
nanometers.
E of one photon. I'll call it E1.
Okay.
So this is a number. It's in joules.
Yep.
Let's say. Or it can be in anything. Oh, sorry. Let me
So-
put it in electron volts.
Okay.
So it's in electron volts.
It's in electron volts. We have it in electron volts. So, okay, and we have an energy density, and we have the field, right?
Mhm.
So it's 1 microwatt per meter squared, but the field itself is 0.1 nanometers squared. So it's 1 microwatt per meter squared multiplied by, converted to, multiplied by 10 to the negative 19th.
Yes. So
Now we have the density for that particular field.
we could. I'll just say this is 10 to the minus
19.
6. Right. Watts per meter squared.
Okay.
Okay, and then this times. So this is the energy density.
Yeah.
I'm writing all of this, but this is the energy density. Okay, it's in units of. It's energy density because it's it's actually called a flux, but that's a whole other thing.
Okay.
Anyway, we can multiply the energy density times the. It's density in terms of area. So if we multiply by an area, we'll get the energy
Yes.
in that area.
Okay.
And so we'll get 10 to the minus 6 times 10 to the minus 19 is 10 to the minus whatever. Wait. Yeah. Okay.
So,
Fine.
yeah, we got it. We got it. We're
10 to the minus 25. This is in watts. So this is the.
Oh,
Now-
and it has the conversion. Well,
What do they
God.
say about time?
So it says how much time does it take before the energy field accumulates 2.4 electron volts of energy. So,
Yeah.
all right. So we have the energy of the photon, and we have the amount of energy in this area. We have to
Uh-huh.
find the amount of time it takes for this energy field to accumulate 2.4 electron volts.
I'm concerned that nothing else says how long things take, right?
Yeah, that's part of the problem. Actually, there is something right here. So it talks about light consists of a collection of particle-like photons.
Yeah.
So it has a formula here in terms of photons per second. The only problem is this flux looks a little complicated.
This one's just plugging back. This one is changing the meters. Gonna let us.
Wait, what? This is strange.
You are all of us thinking about physics right now.
So, can I see the?
You could take it if you like.
Oh, sorry. Okay, sorry. I completely missed something. Watts is a unit of power. Sorry, I was like, there's no other time anywhere. Watts is joules per second.
Oh, okay.
Sorry, I don't know why. Yeah, I was thinking joules, and I was like, that doesn't make any sense. So, this is by the way just a fact. Watts, the definition of a watt is 1 joule per second. So it's a unit of power, meaning it's a unit of energy over time. Okay, so now we know how many joules. We know that the whatever we want receives this many joules per second, and we know the energy of one photon in.
That's your work thingy.
What was that?
I don't know.
So,
You're too.
so we have here that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules.
Yeah. So
We
can
have the amount of energy per photon, and we have a rate at which this field accumulates energy, right?
Yeah.
So in that case, all we have to do then is, go ahead.
So my question is, why do we need the energy of the photon at all?
Because we're trying to figure out the rate at which this system collects energy, not photons.
I know. So then we don't need photons. That's what I'm saying. This you can find how long. So this you can convert to some number of electron volts per second. It's just a conversion from joules.
Okay.
And this, you can just say, well, how long does it take to get some number of electron volts? You can just figure that out.
Maybe it's
So nowhere do we need to know anything about the photon energy, which I guess that's fine. It's just weird that they would ask that.
looking at the wording of this question. It looks like it could just be two questions that just got lumped into one because it's on the same
Okay.
subject. You'll
I
take
would
it?
agree with that.
Okay.
Because as far as I can tell, you do not need to. The first part is fine. It's a separate question.
Okay.
And looking at the
So in that case, if it takes that much, so two
no, so these answers are not really correct. I mean, maybe the description is correct, but the units are not correct. Obviously, it says this. Okay, let me just tell you what it says. The first sentence says to get 0.24 electron volts, we need only one photon. I don't know what that means. I don't know what you're talking about. So, yeah, I don't
Keegan,
know what
credit
that
where
possibly mean.
Well, because it's saying you're accumulating 2.4 electron volts of
Yeah.
energy.
Yeah.
So that's one work order. That's one work order, essentially, which is one photon.
Well, no, because if you just assume this is all continuous, so pretend there's no photons, it's just a continuous amount of energy,
All
right?
right.
Like it's just a stream of energy. That's what this is saying. When they say the energy density,
Okay.
this is a stream. This isn't bits, right? All the rest of the question still makes sense. That's my confusion. Is that everything makes sense and is doable, and I can just get an answer without dealing with the fact that there's individual photons. So I mean, I guess that's fine. It's true. You could.
One of those things they just throw into message.
They might just do it because they're like, well, later they could say how many photons per second. Oh, do they say that? No, they don't.
Of course not. Maybe he meant to.
How, calculate the time required for an optical field. Okay, well, they could literally say at the end, what's the photons per photon flux? They would call. I mean, they would say how many photons per second, and you would just divide this by the energy per photon. You'd get photons per second. So that's a very reasonable thing to ask. They don't ask that. So as far as I can tell, you just need to do this. Like you can just, they're separate questions.
I think maybe this is what Professor Z is trying to get us to do. Because a lot of the history we talked about involved scientists puzzling over the answers instead of
Right.
the process to get the answers. Maybe he's trying to get us to puzzle over the answers to these problems instead of how to actually solve the problems.
He succeeded.
So wait, what's the what's like
Yeah.
the final thing that we need for this problem then?
It would be a time t. So you have a rate, joules per second, and you have a rate. So we went from energy density, which is you could write this as 1 microjoule per meter squared seconds, which sounds like why would I do that? But it actually is kind of nice because now everything's in units that we need them at the end. Of course, joules has meters and stuff in it too, but this is where now we can say, well, we know how much area we're going to capture. So if we have this field, this is the amount of energy per meter squared, which is an area, for every second, right? So it's the flux, right? Like sunlight would have this type of form, right? I mean, it's an optical field. It's like sunlight, any light. They tell us the size of the area, so we know m squared. We know the area. Therefore, if we multiply this by m squared, we get, which is a, we get something in joules per second. So we get this joules per second, which is the flux through that actual area, which is some small area. Once we know the joules per second, we could also just convert whatever the target, that 2.4 electron volts or whatever it is, to joules, and we just say, okay, well, we want to get 10 to the minus whatever joules. How many seconds does that take? Well, then you just divide. I mean, it's the same as like V is d over t. If V is a rate, and d is a cumulative distance, and t is time.
Mhm.
So to find the time, you get d over v. So that would just be d is the accumulation, the energy divided by the rate, and you'll get the total of the time. And now you can do that of course. So the target is in electron volts, and this is in joules. You could convert either way. Obviously, it should be the same time. So convert this to joules, or this to electron volts. And again, nowhere in here does it matter that they're photons. I mean, when we talk about sunlight, talk about the energy, the watts per meter squared of sunlight, or all this stuff, and then therefore the time it takes to accumulate energy. None of that has to do with the fact that there's individual photons, because they're treating this as continuous. Later, of course, they could say Oh, so if they said how many photons, we would need to know the energy, or sorry, we would need to know the wavelength of the photon. So if they said just how many photons, we wouldn't be able to answer it. If they just said how many, assume this light that we've been talking about that's streaming, sunlight, whatever. Let's say it's all like yellow light or whatever, right? We would just look up the wavelength or the frequency of yellow light, find the energy per photon, and then we could just divide it by the energy we want, or no, by the rate, and we would get the photons per second that would actually be happening. Of course, the same amount of energy per second, same amount of flux for different photons is different for different colors of light, and would be different amounts of photons, because some of them are very dense with energy, and so we don't need as many of them to get this, and some of them are, so for X-rays, for example, you wouldn't need as much to get the same energy density, same flux, and if they were radio waves or whatever, you need a lot of them because they don't have as much energy each. So hopefully everything I'm saying is more informative than this homework question, because you don't really have to know any of this for the homework question.
Okay. So we take care of that.
I guess, okay, this isn't important, but let me just, I think I could see why this question is just trying to get you to go from, the first part is literally saying particles of light, talk about them. The second part is saying continuum of light. So I guess it's kind of interesting that they're asking you two things at the same time that are literally about different versions of looking at light.
Two different versions of the same thing.
Yeah, they're the same, right? You could think of it in a macroscopic level, you can think of it as a continuum. And a microscopic level, you can think of it as a particles, or little, quanta. They call them quanta because particle is a little ambiguous what you mean by particle, but quantum is just means an object that you can't separate.
I thought that was an atoms definition, something that can't be cut.
Yeah, but you can cut atoms. That is what atom
cut them
means.
now, in 300 BC, it wasn't really the case.
No, but you could have if you had the right equipment back then too.
Really? Like what?
Well, sure, but nothing changed physically. The atoms back then were the same as the atoms now. It's just that they didn't. Anyway, the point is that even if you say particle, like an atom, like a nucleus is a particle, alpha particle, but that's not. There's made of things, right? So.
I'm getting a distinct image of you interrupting Democritus's speech, like in a toga, just saying, "Wait, actually, no, you can cut an atom
if we had the right equipment."
If we had the right equipment.
I guess this kind of. Oh,
No,
sorry.
I didn't.
This kind of goes into 8, which says consider 2 500-watt light bulbs, one
Yes.
UV and one infrared, emitting at this wavelength and this wavelength,
Yes.
which emits photons at a higher rate.
There you go. Yeah.
So then you take.
Right. It would be part of this question where, you just say, well, they say they're the same intensity or something?
500 watts.
Oh, okay, yeah. So they're both 500 watts. Watts is in joules per second. Yeah, so they're literally giving you this number, but it's not this small. And they're saying, yeah, right. And you just say which emits photons higher. Well, the ones that have lower energy photons, obviously there's more of them because the total energy is constant. For you can just say over 1 second, how many joules is there? 500. And then it's a little easier.
Yeah, so you can use that wavelength to find your energy.
Yes. Energy per photon, and then,
Do I have to take the final now that I found a significant error in the book? Probably. Don't answer.
Probably. You're free
Even
to ask.
more so now.
No.
You're free to just not take it and see what happens. But I wouldn't recommend that.
I once heard a story about a fellow who didn't even try to take the exam. He just taped a $5 bill to the front of it and just hoped for the best.
And fact. $5 is not very
No, that's
for
not that
professors.
I think he was assuming that the TAs would grade it. Apparently, he
Oh,
meant
I
a lot
see.
more money to them than the professor.
Yeah,
Yeah.
that's true.
$5
Still,
is
though.
quite a bit to you.
$5 is like a
Smash.
coffee.
You like your coffee, don't you? Oh yeah, you get it for free.
Right, so
$5 for a cup of coffee, though. That's pretty rough, actually. What do you?
I mean I don't pay $5, but
Here's a question.
Yeah.
What we have to do to increase the photoelectric current.
To increase, that's just the whole question?
That's
Eight
number
point-
one.
That's number one. Oh.
Yeah, of 11.
What can you
assignment's
do
11.
to increase the photoelectric current?
Yeah, so it's weird because we can increase the light intensity, but we never really talked about light intensity. I don't know really what light intensity is.
I mean, so first of all, I don't totally know what photoelectric current is. I assume that just means the amount of electrons coming off.
I
guess
got it.
I wouldn't really call it current, but
I googled it. If the frequency and intensity of the incident radiation are fixed, the photoelectric current increases gradually with an increase in the positive potential on the collector electrode until all the photoelectrons emitted are collected. Did you get that?
yeah, that's not very helpful though.
Yeah.
For this question,
Okay.
that's overkill. Because the current is, I assume they just mean. Oh, okay, I see what they're saying. So we talked about the energy of the emitted photoelectrons. Photoelectron just means an electron that is emitted by the photoelectric effect. Would be this minus the work function, right? This means that if and I'm going to say something that you're going to be like, yeah, you said this like 100 times. This is for one photon that hits a metal and overcomes some work to free one electron, okay? Now, that's energy, right? If you increase the frequency of your photons, you're going to get more energy coming out, right? But if you just increase the frequency, you don't increase anything else. You don't increase the intensity of the light, the amount of photons. You're just going to get higher energy electrons. But if you're interested in the electric current is not different forever. Every electron has one charge. So if you want to increase the electric current coming off, you have to just get more electrons. There's no way around. You can't give them different charge. They don't. That's impossible.
Okay.
They literally have to have. So to get more electrons, you have to just every one photon gives you one electron by this. So you just have to give more photons.
Okay, because I wrote you have to increase the light intensity, but I didn't know.
Yes, that's fine.
Okay.
The point is that the wrong answer would be increase the frequency of the light or
that's
decrease the wavelength. Those would be wrong answers because they don't give you more electrons.
What happens? What if let's say we have all this extra energy? What happens to it?
Extra energy.
Once we've released one electron.
The electron gets it.
Oh,
so-
the electron just takes all.
Yeah, it takes the extra. So the electron uses up energy to escape from the whatever the bound state that it's in, and it just has that energy. So it leaves faster.
Oh, okay.
I guess. Well, it just has more energy.
Okay.
Let's not say it leaves faster. I don't know about that. It has more energy.
Okay.
Yeah. So all of the energy is still conserved in these processes. So that's what happens.
Right. So how would we increase the photoelectric current then?
It would be you'd have to have literally more photons.
More light
More
intensity.
Okay.
More
we're-
photons, not higher energy photons. That doesn't help you.
Just more of them.
Yeah, because each one gives you one electron, right?
But
No matter what the energy is, they get one each. So if you want more electrons, which is to give you higher current, you need more electrons, right? To get more electrons, you literally just need more photons. Of course, they all need to be high enough to overcome this, but as long as they're that, you don't care too much about the energy. You just care about having as much of them because you want the electric current to be high.
I'm good.
If you want the outgoing energy to be high, then you could increase the frequency. That would be fine because you still get all the electrons, like you were saying, the electrons leaving have that extra energy. So if you give it more frequency, if you give the incoming photons higher frequency, the electrons coming out will have more energy, so you'll get all that energy back. Like it's, you won't get all of it back because some of it goes to this, but you'll get more energy back if you turn up the frequency.
Right.
But if you turn up the frequency, you won't get more electric current because you won't get more electrons. You have to literally give you more photons, which means more. Anyway, I'm not gonna say. Yeah. Does that make sense?
That's a really good way to compare it.
Kind of. It's not you. It's just I'm trying to relate this to like electric current.
Yeah, it is
Or
electric
like
current.
yeah, but in electric current, if you want to increase the current, you need
Yeah.
a larger battery or you need more power. But the truth is, you just
Well-
need more electrons to increase the
And I keep adding
current,
these,
right?
I'm just gonna have that more.
Yeah, because this is this energy here, what you can change by changing the
But-
photons,
I
this
only need
energy
these 3
is
years
just the
to
energy that
release.
the energy that each electron has.
Okay.
The energy that electron has nothing to do with its electric charge. So if you want more electric charges to come out, which is more current, you need to have just more photons interact,
The one.
right? Because each photon gives you 1 electron.
And
It's a circuit is a slightly different picture.
number 2, page 145.
What do you mean the largest possible wavelength?
So it says calculate the largest
Yeah,
wavelength.
yeah. I'm saying, what do you mean by when you said you could look up?
I think maybe I'm just complicating this. Never mind.
Well-
It's easy enough. I look up the.
You look
I
up the
electron
5.
for 5
Yeah.
of them, right? And then I find I use HC over lambda, calculate the largest wavelength we need to surpass that, and we're done.
Yes.
Yeah.
Easy enough.
So it literally
we
would
could
be.
put that, we could put that in an Excel spreadsheet.
Yeah.
It's easy enough.
Okay. I wouldn't have thought of doing it like that, but yes.
Well, we're literally repeating the same equation over and over and over again
Yeah. I mean,
for 5 of them. So just a different input.
that's true. I mean, it would just be. This is the kinetic energy of the electron. Then when it leaves, if you set this to be 0,
Mhm.
you're just saying that it's just barely enough.
Okay, so the largest.
So it would be
required-
when these are equal. Yeah.
Okay.
So and then you just so it's what you said. I'm just writing it on the board. But yeah.
All right.
And the reason they say largest required is because there's a minimum energy you need, right? Because, as you can see, it's right here. It's this.
Yeah.
But the minimum energy happens when the wavelength is below a certain amount. Because remember, longer wavelengths are less energy.
Okay.
So if you have a sort of, you can imagine like the wave gets like tighter, like as it gets sort of compressed, and right, it gets more and more energy, and so there's a maximum value where if you go farther than if you stretch it more, you'll have not enough energy. So that's why. It's just because it's in the denominator.
Okay.
It sounds a little weird, but
All right. For number 4, an X-ray of wavelength 0.05. The questions are 1, 2, 4, 5, and 8.
okay.
For number 11, for assignment 11. All right. So an X-ray of wavelength 0.05 nanometers is scattered by a free electron. Under what conditions does it transmit the maximum amount of energy to an electron?
Wonder what conditions does it transmit the maximum?
The maximum amount of energy to an electron.
Oh. I believe you would just use the Compton.
Compton scattering?
Yeah.
Okay, so in that case, 0 angle of, it would be cosine of 0?
Well, no, because you want to transmit the maximum to the electron.
Okay.
So the energy is conserved, right?
Okay.
You have the incoming photon has some energy, and the outgoing has some energy too. And you want the photon to get the minimum amount of energy, right? Because if you want the electron to have the maximum amount, then
Okay, so Compton scattering is,
yeah.
Lambda has lambda.
It's probably when the, I mean, I don't see why, I think it's just when it's 180 degrees, because that's when the, actually, yeah, you want to, you want to transmit the maximum amount of energy to the electron. If you had 0 degrees, if it just kept going, that's transferring 0 energy to the electron.
okay. So we're
Right.
looking at, so for Compton scattering, we're talking about delta lambda is equal to h over mc times 1
Yeah,
minus cosine theta. Okay. So what this equation tells me is that under these conditions, h over mc 1 minus cosine of theta, that changes the wavelength.
Yes.
And if the wavelength changes, inversely the energy of the wavelength also changes.
And yeah, exactly.
All right, so, and because Compton scattering is related to the photoelectric effect, whereby photons transfer their energy to electrons, allowing them to become active.
It doesn't really relate to the photoelectric effect.
Okay,
Photoelectric effect, what you said is correct,
just not really.
but it's not called the photoelectric effect. The photoelectric effect is a very specific thing with metals and stuff.
Okay,
That the fact that they interact is another true important property.
okay.
But the Compton scattering gives you the interaction.
All right, so in this
You don't-
case,
yeah.
so what the Compton scattering is telling us then, so delta lambda means that
Yep.
the energy of the wavelength of the photon changes.
Yes.
Right. The energy of the photons, since energy can't be created or destroyed, goes to the electrons.
The incoming energy of the photon goes to the outgoing photon plus the electron.
Okay, so in this case, because it says an X-ray of wavelength, etc., is scattered by a free electron, that means that the energy from the photon goes to the electron.
Yeah.
Okay.
Well, yeah, it goes between the scattered photon and the electron.
Okay, so in this case, would we be saying then that it'd be cosine of 90, that it gets scattered in a completely different direction?
Well,
That would allow the greatest transfer of energy to the electron, right? By the scattering?
no.
Okay.
How are you getting 90?
Wouldn't it be 180?
I think
Right,
it would
it's
be 180.
right, 180, because it goes backwards, that's right.
You would have to look at the formula. You would see when. I mean, you want the wavelength to be maximized.
Okay, so
You want the wavelength to increase a lot, because if the wavelength increases a lot, the energy of the photon would decrease a lot,
Yeah.
and therefore all the energy would go to the.
okay.
So therefore you want delta lambda to be maximized, right? And that's maximized when 1 minus cosine theta is maximized, which is when cosine theta is
180.
minus 1, which is theta is.
Okay, so
180. Yeah.
question 4 in the at the end of the chapter is literally question 8.4, which we went over earlier.
Fair enough.
Yeah.
I
No, I
believe
mean-
you.
Yeah, so,
That sounds like something that would happen.
okay, so, what's the new wavelength of the scattered X-ray? Easy
Yeah.
enough, constant scattering. Part B, the percent of the original energy transferred to the electron during the collision.
Right.
Also easy enough.
Right. If
Okay.
you have the Compton formula tells you about the wavelength before and after, and you know a formula that tells you the energy from the wavelength, and therefore you can get all the energies you need.
All right.
You can't get the energy of the electron directly from anything, because we don't know any formulas for the kinetic energy or anything of an electron. But you could just subtract them, of course, and get the energy transferred to the electron.
Okay. Number 5, monochromatic light of wavelength 2.4 picometers collides with a cloud of free electrons. Find the wavelength of light scattered at 45 degrees and 90 degrees. Same thing, constant scattering.
Yes.
Okay.
Wait.
We talked about
Can you say that again?
Mono-
Sorry, you say the very beginning again.
monochromatic light.
this. It was
Yeah.
the whole like 2.4.
Oh, that was the okay.
Yeah, that
So we
was
did
the
that.
whole
Yeah.
picometer. Is it negative 12 or negative 9?
Yeah. I was just making sure the
And we
angle wasn't.
found out that his equation was wrong.
Yes.
That was fun. Good times.
Good times.
Good times.
Reminisce.
Consider this is the last problem.
Mhm.
Consider two 500-watt light bulbs, one UV and one infrared, emitting at 400 nanometers and 800 nanometers respectively. Which emits photons at a higher rate? Find the ratio
Yes.
of their emission rates.
Yeah.
Okay. So we have two 500 watts. Okay, so here we have energy, 500 watts from each.
Uh-huh.
The only difference between the two of them is wavelengths. Which emits photons at a higher rate? The one with the greater frequency, right?
Yes.
So in that case,
No.
oh, dang it.
So remember, this was this thing we were talking about. The thing I was saying that is not this problem, but then we found out it was the next problem.
Oh, yeah.
If there was some rate, right? If there was a constant rate, if you find the energy of one photon, if you know the wavelength, then you could find the energy of each photon. And if each photon has less energy, if each photon has a smaller frequency, then it has less energy, right?
Okay.
And if it has less energy, then to get the constant energy rate, which is 500 watts, you would need more of them.
But when it says two 500-watt light bulbs, does that
Yeah,
mean
they're both the
500
same energy.
Does that mean 500 watts per photon or 500 watts for all of the photons?
That's for all of the photons.
Okay.
Yeah. So it could be more or less photons. You don't know how many, but you do know the energy of each individual photon, because they tell you the wavelength or frequency of the thing.
Right. Okay.
So yeah.
So the one that emits photons at a higher rate. That would be.
Frequency, not rate.
So the one with the smaller wavelength would have the higher frequency. No.
That's true, but
We're not paying attention to frequency and intensity, right? Sorry, frequency and intensity aren't related.
what is intensity?
Intensity,
I know what it is, but I don't
assume
know
that
if that's what you're talking about.
I think that intensity is the amount of energy per photon.
I would just perhaps, but let's
Okay.
not say that.
How do you define intensity?
Well, I wouldn't define intensity for this problem.
Okay.
It is defined as this, actually, because it has meters. We don't need meters.
Okay, so
Yeah,
the amount of energy in a certain area.
Yeah, that would be. I would call it.
That's
You're getting a little out of the scope of this.
Yeah, this is actually you're
You're thinking
defining
of
some very important things that are overkill.
Yeah.
okay. So
These are all very 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 easily confused quantities for me personally. So I don't know. I don't even remember. This might be called flux, and this is called intensity. So this might be intensity. That's fine. What I would just say is, I mean, just imagine. I mean, it's you know, they're just raindrops, right? Just imagine raindrops. I know I sound like I'm crazy, but just
okay.
imagine that they're raindrops, and you're gonna. You say two like, you know, there's like two like your hose that has like a mist, and then it has like a like a sprinkler, right? And you say, well, they're gonna fill it up at the same rate, fill up a bucket at the same rate, right?
Okay.
Because the same amount of water is going through the hose, right? So the total amount of water is the same. Well, if you know that one has very small raindrops, there must be a lot more of them. And you know the one has really big raindrops, or drops of water, then you know there can't be that as much. There's supposed to be way more of the small ones, because there's the same amount of total
photons
water.
for the one that has the lower.
Right. When you do a mist, there's a ton of little raindrops. When you do what the other one is, sprinkler, I guess there's not as many, because the total amount of water through the hose is constant, which means that's the total amount of that's the watts. So the watts is the same.
So the 400 whatever one is emitting more photons, correct? Because
Yeah. What's the other one?
800.
The 400 wavelength.
Right.
Yeah. Well.
So like to get to the 500 watts that it needs, it's
Yeah.
emitting more photons, correct?
No, the 400 has more energy because it's.
It's asking
which has
which
the
one's
great.
emitting them at a higher rate. So like to maintain that 500 watts, it's asking which one, the 400 or the 800, is emitting at a higher rate.
I believe it would be the 800, because the 400 would have a.
I mixed that up.
Yeah, it's very easy because of the number.
Yeah.
If it told you the frequency, it'd be much easier.
Yeah.
But so you basically, what I would do
Yeah.
is write
For some
the
reason I thought
energy.
that was the frequency.
No, I would just write the energy and then forget about the.
Yeah.
It's very confusing if you think of. So just write like E 400, and that's gonna be confusing. Is h over lambda, which is gonna be some number, and then E 800
Mhm.
is some other number
Right.
too.
Which means that
It's
one.
too many
was
numbers
the-
now, but you know what I mean. And now you'll see that one of these is bigger than the other one.
Right.
If it's a bigger energy, then it doesn't need as many photons.
So
That's energy per photon.
E800 has more photons.
Yes.
Okay.
And E400 has less photons but more energy per photon.
Yes.
Okay, I think I understand what you mean.
And it should be
Because they're producing
double, I believe.
Okay, so yeah, like you were talking about the rainstorms. You've got one
Yeah,
that
yeah.
has less drops, but they're bigger. You've got
Yes.
one that's got smaller droplets, but there are more of them, for them to produce the same amount of water in a
Right.
given amount of time.
Right. But the only reason you know that they have to produce the same amount of water is because they told you the intensity was 500 watts, or sorry, I shouldn't say
Like
intensity.
filling up a gallon.
Yeah, they told you the that's joules per second, or that's the energy. That's the the energy of each drop adds up to the total energy that comes out per
Okay.
second. So pretend it's over 1 second.
You're using metaphors, Keegan. I feel so proud.
I
Okay.
tried.
All right. So which emits photons at a higher rate? The one with the lower wavelength. Sorry, the one with the higher wavelength. The one with the greater wavelength.
Perhaps, but I
800.
wouldn't say it like that. That's it's very hard to imagine that. I would say the one with the smaller energy.
Okay.
The one with the smaller energy
Emits photons
has
at
to
a
have
higher
more to keep up.
Okay.
I would say that.
So find the ratio of their emission rates.
Let me say, I admire you for doing this in your head, but it's very hard to do it in your head.
Okay.
Even I have something to write on.
I'm trying to
So
think about.
I would write. If you write these out, you'll probably find that they're a lot easier
Okay.
than they seem like they're causing you.
All right.
Because if you literally write the amount of energy each one has, and then think, and then you'll have to think, okay, well, what's the ratio? Well, if one has, I mean, I guess it's sort of obvious to see that one of them is going to have double the energy the other one has, right? I'm not even want to think about which one. One of them is going to have double the amount of energy the other one has. If each photon has double the amount of energy, you literally are going to have half as many to have the same total power. I should call it power. That's really power. Flux is probably, this is flux. Intensity is something related to this. I don't know what it is.
Okay.
I'm
So-
not going to say that.
All right.
You can always say like number of photons or energy per second. You can always say things like that. Power is just energy per second. But yeah.
So the problem with that formula right there, E is equal to HF minus phi,
Mhm.
is that it tells us about the energy of a photon, but it doesn't tell us about how often they're emitted.
Energy of an electron.
Energy of an electron, excuse me.
Yeah. You know that they're emitted. I mean, this is one electron emitted when one photon hits it.
Okay.
So you kind of do know about the intensity. It's
So in
the
that case-
same as the intensity of photons.
So in that case, the rate is literally 1 to 2, right? One is a 400 nanometer. Excuse me. One has a 400 nanometer wavelength. One has an 800 nanometer wavelength.
Yeah. That's true. It doesn't really have to do with this though.
Okay.
But you're right that yes, one is double the amount of.
That's the rate. So 1 for 2.
Yeah, one is double the amount of energy of the other one. So to get a constant amount of energy from both, one of them, the lower energy one, needs to emit twice as many. Right?
Okay, so it's a linear correlation then.
Yeah.
Okay.
Yeah.
All right. Backtracking a little bit to question 8.2 in the chapter itself.
Yeah.
So consider an electromagnetic wave of visible light with wavelength 500 nanometers and a flux of 1 microwatt per meter squared. How many photons per second are arriving in an area of 1 square centimeter?
Right.
So converting 1 microwatt per meter squared to 1 microwatt per centimeter squared.
Okay.
is basi-
Or yeah. Okay.
Yeah.
Or you could convert the centimeter squared to meter squared.
Oh yeah, that's definitely true. But basically, we just
Yeah.
have to.
Yeah. Do one or the other. Yeah. And then you multiply them, you get a watts, right? Microwatts or whatever.
All right, and then after that, yeah, it's just.
Yeah, it's actually the same as this. And then there's the final step that I said, but we didn't need to do for some reason, which is just you just say, if you have electron volts per second and you have electron volts per photon,
Mhm.
you could find photons per second.
All right, so we find the energy of the photon with the given wavelength, and from there, okay, easy enough.
Yeah. It's some mostly dimensional things,
Okay, we got through all of them.
Nice.
Yeah.
Was that fun?
About as fun as I could hope for it to be.
Well,
Did
there you
enjoy
go.
it?
Did I enjoy it?
Did you enjoy it?
Yeah, it was alright.
All right.
Yeah.
Whenever people say, yeah, it was all right, or yeah, it was fine, or yeah, it was okay.
Yeah.
Yeah, it's like you're using it to describe Thanksgiving.
Well,
It was about as pleasant as I could have hoped for it to
good
be.
as it gets.
Which wasn't very much. Yeah,
No,
see,
it was
that's a good one too. It's as good as it gets.
It's just that these problems are not the most fun things you can do. There's a class you have to take when you're a physics undergraduate, when you're in your sophomore year, called Modern Physics, and it's one of the most boring classes I've ever taken. It's just all about special relativity and this photoelectric effect and energies of photons and fluxes and intensities and stuff, and it's just a bunch of nonsense, stupid, boring stuff. So it's really not fun. And then later, when you take things like
The camera's still
actual
rolling,
relativity or
right?
something, it is rolling, yes.
Okay, keep going. Never mind.
Well, I guess the people will not hear my story. I'm going to end now.